Section 2.5 is called implicit differentiation. Okay? Remember, the word differentiation just means derivatives, finding derivatives. I want to define what we have been doing versus what we're about to do. So what we have been doing is called explicit differentiation. Explicit is taking a derivative of y in terms of x when the equation can be simplified with y equals on one side and everything on the other side in terms of x. This is exactly what we've been doing. In fact, we haven't even had to simplify it to that form. It's just been given to us in that form. Y equals this. F of x equals this. And it's all in terms of x. That's called explicit differentiation. Okay? So implicit differentiation means taking a derivative of y in terms of x when an equation cannot be simplified to y equals, or maybe it's just not so nice if we simplify it to y equals. That happens occasionally as well. In order to use this method, we have to treat both x and y as variables, and then use all the derivative methods that we have learned. So there's no new rules. There's just a way to apply them in a different situation. So jot those details down. The first one? Yes. It's not a circle, it's actually hyperbola because it has a subtraction in the middle instead of an addition. For addition, it would be a circle. Okay, does everybody have those details written in? Okay, so Dawson was noticing that this equation looks like an equation for a circle, and he's close. It is a conics. It's not an ellipse either. It's actually a hyperbola. If you don't know what I'm talking about, it doesn't really matter which of these things it is. But the sign in the middle being negative actually is what makes it a hyperbola. Okay, here is a case where we could solve this for y, right? You could throw the x squared on the other side, get rid of your negative, you could square root. The problem, there's two problems, not problems, but there's two difficulties in doing that. One difficulty is that you have to take a square root and then you're going to involve a chain rule, right? Because you're going to have something underneath a radical. That's not really a problem. The bigger problem is that you're going to get a plus or a minus when you take the square root, which is going to make it messy. Okay? So what I want to show you is that implicit differentiation is actually quite a bit easier to work with when you're able to do so in many cases. So here's the deal. As we're taking a look at this function, we're not going to move anything. Everything is going to stay right where it is. And we're going to take the derivative of the pieces just from left to right. So the first piece is something you know and love. What is the derivative of x squared?
2x.
2x, no problem, right? All right, now you're going to pretend like y is just like x for the moment. What would the derivative of y squared be?
2y.
2y. Now here's the catch. It's not just 2y. Because imagine if you had this say y equals ... and you took the derivative, y doesn't just disappear, right? What does y become?
By sub 1.
Y prime, or dy dx, right? So it becomes this y prime thing. Here's the deal about that. I don't like that notation very much because that notation almost starts to make it look like it's got a power of 1, or it might just sort of get lost in the mix. Another notation that's a bit friendlier to work with here is dy dx. So I'm going to be using this notation. It means derivative of y with respect to x. So anytime we take the derivative of y, its derivative is dy dx. So if you take a look at y squared, what happens is we have a chain rule. The outside part's the power 2. It's the part we already did. We pulled the 2 down. We rewrote y. It has a power of 1 now. But the derivative of y itself, the part that's inside the square, is dy dx. So anytime you're taking a derivative with y in it, you're going to get dy dx as part of the value. So this right now has dy dx beside it. And then on the right-hand side, what's the derivative of 25?
0.
That's 0. Now, calculus is done. That's the derivative implicitly. However, in order to actually write it out the way it was asked for, that is find the derivative y prime of x or dy dx, what do you have to do? Well, you need to solve for dy dx, right? You have y prime equals as your answer. Now, we're going to do that. So we're going to move the 2x, move the 2y. We're going to separate them. So I have 2x equals 2y dy dx. And then what do you think I need to do with the 2y? Divide it. Yeah, we're going to divide both sides by 2y. So of course the whole point is that those two cancel out. I'm left with dy dx on the left. What do you suppose that it simplifies, I'm sorry, on the right. What do you suppose it simplifies to on the left?
X over y.
It's just x over y. And aside from the weird dy dx thing that sort of reared its ugly head a little bit, that is way a lot easier than working with radicals and pluses and minuses and chain rules the way that we would have to if we actually solved this for y. It makes our lives easier. Okay? Now, the one thing it doesn't do is it doesn't give us a form of y prime equals or dy dx equals with only y's on one side. Excuse me, with only x's on one side. It's got x and y involved, correct? So that's a little bit messy. It's not too bad if we were wanting to evaluate this. As you've noticed in your book, they always give you the xy coordinate pair. So that's actually fairly friendly. That's something your book does. It's nice. But we can still work with this. Okay, let's try another one. This one truly becomes a lot more complicated because we've got division with y on the left. We've got a square with y on the right. Solving this for y becomes virtually unattainable. Okay? It's got so much algebra involved that, like on the last one, we could do it. We could solve for y. It wasn't terribly complicated. It just wasn't obviously pretty to do it, right? Here it becomes terribly complicated to solve for y. Now, I do suggest that we change something so that we don't have it be as complicated as it looks right now. I've got I have a quotient on the left, correct? Why don't we just multiply by y so I don't have a quotient? Wouldn't that make life easier? So there are things you can do to make life easier as well when you're doing implicit differentiation. Just because it's given to you in one form doesn't mean you have to work with it from there. If you do work with it from there, it'll be okay. You're going to get the same answer. It's just going to be a little bit more complicated to do. Bryson?
On the gateway, is it okay if we rearrange things before we actually use the calculus?
Absolutely.
Or let's just use the calculus?
You can definitely rearrange things, and then there are a couple places where you probably will have to. Yes. But clarifying still, too, it won't be this, right? Because there won't be any implicit differentiation on there. Okay. All right, so my suggestions first, let's just multiply by y. So I have x plus 3 on the left, and I have 4xy plus y cubed on the right. Now it's a give and take. I mean, I got rid of the y on the left, so the derivative on the left-hand side is going to be very easy. Unfortunately, that does make me have a product right here, right? X times y would be a product, so I do end up having a product rule on the right. So just being aware of that I did complicate the right a little bit more to simplify the left. Let's do the derivative now. What's the derivative of x plus 3? That's just 1, so that's super friendly. Yes?
If you left the y on the outside and used parentheses, would it just be a chain rule?
It would be a chain rule and a product rule because the y on the outside would make it a product.
Okay.
Yeah. So you could do it that way. It wouldn't hurt anything, but eventually you're going to have to clean it up anyway. So I don't know that it's going to simplify anything to do it that way. All right, 4xy, as I mentioned, is a product. I really got to not use this yellow. On this yellow background, it doesn't work very well. Let me try something different, or red. Okay, there's my product pieces, right? I have one piece that's the 4x and have one piece that's the y. So we're going to kind of group them in those two components. And when we do the product rule, we rewrite the first piece first. So the first piece is 4x. And then I need to take the derivative of the second piece. So what's the derivative of y? 1 dy dx. Don't forget the dy dx. That's actually the important part. Okay, that is half of the product rule. The other half says take the derivative of 4x. So what's the derivative of 4x? 4. And then rewrite the second piece, which is just y. Okay? You could pull a 4 out in front of both of them. We're going to clean this up and have to simplify it in a minute anyway, so either way you're going to get the same thing. But yeah, you could. All right, how about y cubed? What's the derivative of y cubed? All right, good. You guys are remembering 3y squared, and then we have to remember the dy dx. Anytime we're taking the derivative with y involved, we're going to get a dy dx. Now, what I want you to notice is that some components of what's on the right, some of the terms have dy dx in them and some of them don't. Correct?
Yeah.
Okay, so the ones that have dy dx need to stay grouped together, and the ones that don't need to move over on the other side with the other pieces that don't. So there's only one piece that doesn't. It's the 4y. So I'm going to move the 4y over to the left-hand side. Everybody good with that? And we're going to leave the other pieces on the right. So now I'm going to have 1 minus 4y on the left. And then I have 4x dy dx plus 3y squared dy dx on the right. Any guess as to what we might do next?
Take out the dy dx.
Very good. We're going to factor out the dy dx. That's why we moved everything that didn't have it. We want the dy dx separated somehow, and we can do that with factoring. So we're going to take the dy dx out by factoring. So if I factor out dy dx, I'm going to have the 4x piece plus the 3y squared piece.
And then you can divide by that.
Yes, exactly. Okay, and then because I factored, these two are product, right? That's what I have as a product remaining. And so the piece that I don't have the dy dx in now can be divided to the other side. So I have dy dx equals 1 minus 4y over 4x plus 3y squared. Now, a couple of things. You might be looking at that and go, well, can I clean up any? On this one, the answer is no. You should look at the coefficients, see if there's any factoring you can do with coefficients. Like if all of them were even, we'd divide them all by 2, right? You should look at the variables. If they all had an x in them, we would reduce them all by a factor of x. We'd factor out that x, divide it out, basically. Okay, we would do that. If you had any fractions inside of fractions, that's like a big no-no. We don't leave fractions inside of fractions. You'd have to clean that up. Okay? So this one doesn't have any of those kinds of things going on, so we're good to go and we're done. Right? Okay. Here's another one that if we were really very so inclined, we could solve this one for y. It would not be pretty, but it would be doable. We're going to do it, obviously, with implicit differentiation. And what you see on the first piece is you see a product, right? X squared, y squared. So we're taking a look at this as a product. What do I do first?
X squared.
X squared. Okay, what's next?
2y dy dx.
2y dy dx. That's the derivative of y squared. 2y dy dx. And that's half of the first piece product rule. Okay, what's the other half going to be? And then y squared. Excellent. Now, sometimes we get so carried away with all of the difficult stuff that we forget some of the easy stuff, so don't forget the easy stuff. What's the derivative of 37?
0.
0. I have people who occasionally get so concentrated that they just do plus 37 and keep going. So be careful about that. There's plus 0 here. You don't have to write the plus 0, but I will for the moment. And then what's the derivative of 4x on the right-hand side?
4.
4. Yeah. Okay. Now, the nice thing on this one is there is only one piece with a dy dx in it, yeah?
Yes.
So everything that doesn't have dy dx is going to move. The piece that does is going to stay for the moment. So I have x squared. I'll put the 2 in front. So 2x squared y dy dx equals, I have a 4 on the right already, and then I'm going to move my 2x y squared to the right with subtraction. And then what's my next step? Yeah. Divide by the 2x squared y. So I have dy dx equals this piece here. What do you notice? Yeah, every term has a 2 in it, right? Or a factor of 2 in it, really. So I can factor out a 2 from every term and reduce all of these. So that will leave me with 2 minus xy squared over x squared y. Can I simplify any of the x's or the y's? No, why not? Yeah, this 2 in the numerator, this piece doesn't have the x or the y in it, so it doesn't have an x or y in all 3 of those pieces, so we can't do that. Okay, any questions on that one? All right. Got to get some trig involved, right?
Hey.
Yay! All right, sine xy. It doesn't look like that's all that terribly complicated, but a couple things I want you to be aware of. First of all, the y is inside with the sine, right? It's an inside part of an angle, which means solving this, like simplifying this to y equals, would be really ugly. We'd have to do like an inverse sine or an arc sine function if we were to actually solve this for y. We don't want to go there, okay? You do not know what the derivative of an arc sine function is, so you would be stuck at that point even if you tried. Okay, so implicit is definitely the way to go here. The other thing to recognize is it's not just y that's inside, it's a product inside of that. You guys see that? So the sine rule on the outside means that I have a chain rule involved, the sine and then the angle. And then the angle itself is a product rule. So I've got a chain rule and a product rule inside of my implicit differentiation. Okay, this is a messy one. It doesn't really look as messy as the other ones at the beginning, but it's really quite messy. All right, so let's start with sine as the outside function. If it helps you to see them, put the parentheses around the xy. Put the lines underneath it to recognize you've got a product. Whatever it takes for you to see those pieces, do that. What's the derivative of sine?
Cosine.
Cosine. So the first thing I'm going to do is to write cosine. And just like in 2.4 when I was highlighting things in red like this, I need to have the inside function remain unchanged. Cosine of xy. Okay, it does not change. But then I need to look inside at the x times y, and I need to take that derivative. Okay, I'm going to do mine in the other order. So I'm going to do my x first, but you can definitely do it in the reverse order you wanted. Okay, so the derivative of a product means to rewrite one of the pieces. I usually rewrite the first piece. And then what's the derivative of y?
Y.
dy dx. Plus. And then we'll go the reverse order. So what's the derivative of x?
Y.
1. And then the y as the other piece that remains unchanged. That's it. That's the product rule piece on the inside. Equals. Now what's the derivative on the right-hand side? 2x. Easy stuff on the right. Okay, it looks really messy on the left. You might look at that and say, well, let me just divide the cosine xy to the other side. You could do that. That's one way to deal with it. You're going to have to get a common denominator and clean up things later, so that's probably not the way that I would suggest to do it. Here's what I'm going to suggest. What we want is we want to distribute this to each piece. Now, as I'm doing my distribution, everything that's multiplied by cosine, I'm going to write it in front of cosine because I don't want it to look like it's multiplied by the angle accidentally and get confused on that. So I'm going to write this as x dy dx cosine of xy plus y cosine of xy equals 2x. Next, I can take this piece, the one that doesn't have the dy dx in it, and I can move it to the right-hand side with the 2x. So this is x dy dx cosine xy equals 2x minus y cosine xy. Like so. Exactly. We're going to divide by everything that's not dy dx because it's multiplied together, right? So my dy dx, my pen's not cooperating with me very well today again. Might need to change pens. 2x minus y cosine of xy over x cosine of xy. Please don't think that everything has an x in it. It really doesn't. You can't look at the angles like that, right? That's an angle that's embedded inside of the function. So if you're looking at what do I have in common that I might be able to reduce, you have to look at what's being multiplied by cosine. So there's an x right here on the bottom. There's an x with the 2x on top, and there's a y in front of the cosine xy on top. So none of those have anything in common, so I really have to stop at that point. Okay? Is that all right? Yeah? Okay. Let's take another one where we can actually do something a little bit further along. It says to find dy dx by implicit differentiation. Okay, fine, we can do that. We've practiced 4 of those at this point. And then it says, and evaluate the derivative at the given point. Now, you're going to like that, evaluate the derivative at the given point on these particular problems, because what they usually mean is you have to do far less simplification. And the simplification for these is usually the ugly part. Okay? The multiplying and distributing and cleaning things up to get dy dx alone, and it's kind of ugly. So we're going to take the derivative of this. What do you notice that you're going to have happening on the left-hand side? Product rule. What else do you notice? There's a trig function. Good. One more thing to notice. We are going to get a negative. That's true. Not what I was thinking, but you're correct. Where's the y located? It's inside of the angle like the last one, right? So when we have the y that's inside like that, we're going to have to do a chain rule problem. It's a chain inside.
Can we use the arc cosine?
Yeah. Well, if we did, then we would actually not have the ability to take the derivative.
I mean, calculator.
Oh, the calculator approximates, remember?
Still.
Oh, you guys really just want those arc trig functions, don't you? You'll just have to join me for Calc 2 someday in the future. Oh, man. Well, it would be quite a ways in the future because I'm not scheduled to teach it next semester. I know. Some of you are like, oh, man, what happened? Wait a minute. Okay.
Are you in Ethiopia?
No, I'm just not slated to teach it. Okay, let's take a look. We do have a product rule, right? So the product rule says I rewrite my first piece, x. What's the derivative of cosine of a function? Negative sine. Some of you had already said that I'm going to have a negative. So this is negative sine. Okay, the part that's inside remains inside, negative sine y. But we have y inside. And y is a function of x. So it's y, that is to say, what is the derivative of y? dy dx, right? So this is sine y, and then I need to multiply this by dy dx. That's a chain rule. It's not a very exciting chain rule. It doesn't really look like a chain rule. Y just looks like it's by itself. But anytime y is involved, you've got a chain rule involved. And the y here is inside of a trig function. Okay? The dy dx is not inside, right? Because the derivative of the inside needs to be multiplied by the outside. So the dy dx is not inside, but we do have a chain rule. All right, and then I have plus. Now I need the derivative of x.
Cosine
1.
y.
1, and then we have the cosine y, yes. And this equals what?
1.
0. I knew
Oh,
I'd catch
yeah.
somebody. Oh, man. Okay. Yeah, so make sure you're being aware, don't get carried away. Those constants still need to have derivatives of 0. Okay, so yeah, you could solve this for dy dx, and eventually we will, but I would just plug the numbers in first,
Can we get
simplify it.
inverse?
And you're probably going to need a unit circle kind of mindset here for the moment, or grab a table if you're not sure. So the x value is supposed to be 2, so this is a 2 here. I'm going to put my negative in front of it, just because I've got negative signs. So this is 2 sine of y. My y is supposed to be the angle pi over 3, according to the point they gave me. And then this is dy dx plus cosine of what? Another pi over 3, or the same pi over 3, I guess, equals 0. So you guys need to figure out, or to remember, what the sine and the cosine of pi thirds are. Okay? One of them is 1/2 and one of them is square root of 3 over 2. Do you remember which is which?
Yeah.
Nope.
Sine should be 1 over 2.
Sine should be 1 over 2. I think you've got it backwards.
Yeah.
Yeah, I think that's backwards. So the sine is actually, yeah, good try. Way to put yourself out there. We really appreciate it. Everybody else was like, whew, I'm glad he said it because I was going to. All right, so negative 2. I have square root 3 over 2 dy dx. And then the cosine value is 1/2. Okay, is everybody good with that?
Okay.
Okay. You know, if you weren't sure, you could just try both of them in your calculator. One of them is going to spit out 1/2 at you, right? Yeah, and then the other 1/2 would be the radical 3 over 2. So you could check it that way if you weren't sure.
Oh, that's true.
What's that?
Fraction over there simplified.
It will. Isn't this friendly? There's a 2 out here and there's a 2 down here. That's nice. So we can do that for sure. So this is negative square root 3 dy dx. And while I'm at it, I'm just going to move the 1/2 to the other side. So it's negative 1/2 over here. Then what? Divide by the negative square root of 3. So this is dy dx equals negative 1 over 2 radical 3. Because dividing by square root of 3 is the same as putting it into the denominator that's there, right? Okay, we're not going to leave radicals
Oh,
of...
no negative.
What did I do?
No negative.
Oh, you're right. Good point. Let's get rid of that negative.
I like that positive.
Positives. Okay, we're not leaving radicals of constants that are irrational in denominators. Like we're not going to leave square root of 3 down there in the denominator. So I know that you guys probably did a lot of these back in trig. What did you do to get rid of that square root of 3 in the denominator?
Square root of 3, square root of top.
Square root of 3 on top and bottom.
Square root of 3 divided by 6.
Square root of 3, and this one would then be over 6 because the square root of 3 times square root of 3 is 3 multiplied by the 2. It's there. You cannot simplify the 3 under the radical in the 6 that's not under the radical, right? Please don't try. It won't work. All right? If it's underneath the radical, it can't simplify with something not under the radical. Okay, any questions on this one?
As far as notation goes,
Mm-hmm.
what are you expecting? Like, do you want us to write y prime of x, or?
It's your choice. So your book goes back and forth. Like you can see this, these directions say dy dx. The last directions say y prime. They mean exactly the same thing. So whichever one you're comfortable with using. I'm not going to tell you you can't use y prime. I just think that it makes for a possibility of making an error a lot more easily. So I tend not to use y prime. But I will tell you, I've done y prime and taught y prime before too. I mean, I kind of shy away from it now.
What about when we plug the numbers in? Is there anything you want us to show that that's what we're doing at that point?
No, there's nothing. I mean, you could write down like that vertical bar with the x, y equals or something like that, but there's no expectation that you have to. Yeah. Do you have a question, Dawson? No? Okay, I thought I saw a hand over here. No?
Maybe it was me,
But you're okay now. Okay.
Question.
Yes, what's your question, Meanie?
Cosine over sine, do you like tangent or?
Cosine over sine is cotangent.
There we go.
Yes, it's cotangent. Okay, I think we have time for one more. This one is a find an equation of a tangent line problem. It says to the given graph and graph the tangent line in the same viewing window. We'll see if we have time for the graphing part, but I think we have time for the derivative part anyway. This one, Dawson, do you know what this one is a graph of? This one is a circle. It's a circle centered at where? Close. Negative 2, 3. You have to switch the numbers. Yeah, this circle is centered at the point negative 2, 3. What's the radius? Square root of 37, which is a little bit more than 6, right? A little bit more than 6. Okay, very good. It's ugly. I agree. All right, so we're going to take this. Do you guys want to solve this one for y equals?
No.
No, I don't either. It would be quite messy. It'd be ugly looking, and it's not even centered at the origin, right? So yeah, we could, but we would not like to do so. So this one does have chain rules in it, yes?
Yeah.
Because I've got the powers of 2 on things. So what's the derivative of x plus 2 squared?
2x squared.
2 times x plus 2 times 1.
2 times,
X plus 2.
my pen is having issues with me today.
We get a new pen.
Yeah, I'm going to have to. X plus 2 to the
Times
1. And technically it's times 1. Not a very interesting inside derivative, but nonetheless. The other piece, I've got the same thing going on, the 2 times the y minus 3 to the 1. But the derivative of the inside's not just 1, it's dy dx. equals what? 0. Nobody got caught off guard that time. Good job. Equals 0. This one's really nice because I've got 4 and 1 to plug in. There's no trig in it, no angles to worry about, right? X is 4, y is 1. So this is 2 times 4 plus 2 plus 2 times 1 minus 3. Don't lose your dy dx. dy dx equals 0. All right, so what's the first piece? What's 2 times 4 plus 2? 12. Okay, good. What's the second piece? What's 2 times 1 minus 3? It's negative 4. dy dx equals 0. All right? And then if I throw my 12 on the other side, right, I've got negative 4 dy dx equals negative 12. So what is dy dx?
3.
Yes, dy dx, the slope, that's what I'm finding, is 3. I've got the slope of 3. I've got the point, 4, negative 1. So I can find my line. Y minus 1 equals, my slope was 3 times x minus 4. So y equals 3x. It would be minus 12, and then I'd add my 1, so I get minus 11. Okay. We will graph this one next time and show the point of tangency. We actually won't use a graphing device, I don't think, so we can see how that'll work. And I will have this one then that will be due on Friday, right? Well, not Friday because we're not done. It'll be due, I guess, the following Monday because we're not quite finished with it. Man,